All right, you may have seen the intermediate value theorem before, maybe in a pre-calculus class. And a lot of times, it's a very simplified version of the intermediate value theorem. There are more general versions, such as this one, and I'm pretty sure there are even more general versions outside of this one as well. So let's introduce it and then talk about how it connects with everything, how can we use it, how can we not use it, and so on. But again, it's going to be a little bit different than you have maybe seen before. So I will always be abbreviating intermediate value theorem as IVT. I will usually even say verbally IVT. All right. So what is the intermediate value theorem? Intermediate value theorem says, let f be continuous on the closed interval from a to b. What does that mean? It's continuous at every point in the open interval, and we have one-sided continuity at the endpoints. All right. Closed interval from a to b, and some number z is between, that's my shorthand for between the function value at a and the function value at b. Then there is a c that's in the interval between a and b. Remember, this right here means in. So c is in the interval. C is some number in that interval, some number between a and b, with the function value at z. Sorry, the function value at c, they even sound the same, equals z. So let's interpret this, because this is a lot of words. It means a lot of things, but conceptually, intermediate value theorem is not that complicated. Well, maybe my opinion doesn't count on that. That means that we have an interval from a to b, and this function is continuous everywhere in this interval. Well, this function has function values. So the function is defined here, and we know the function is defined here. It's continuous on this whole interval. So look, z is some number between these y values. Z is somewhere in here. Z is a y value somewhere between f of a and f of b. Let's say z, I don't know, it doesn't matter, but maybe z is up here. So all we're saying is that somewhere in the x value, somewhere in the x range, somewhere in the interval here, there's a c, and I don't know where it is, with this point. In other words, if this function's continuous, I don't know how they're connected, but eventually there's a point with that y value. Maybe it's connected like this. Maybe there's multiple points with that y value. Maybe there's multiple c. There could be multiple. Again, if it's continuous, we have to have a y value at z sometime. Doesn't tell us what the function looks like, just says we have to cross and get that y value somewhere. Because if it's continuous, there's no way to skip it, right? We can't do this, because now it's not continuous anymore. All right, so gotta cross somewhere. That's what we're looking at here. And somewhere there is that c value. I don't know where it's going to be. That's the intermediate value theorem. A lot of times in previous classes, you may have heard about it being for polynomials and only for 0. But it actually turns out for any y value, not just 0. And it's for any continuous function, not just polynomials. But we do now know that polynomials are continuous. Polynomials and rational functions are continuous everywhere on their domain. All right, so I still don't know how this page got here. Let's go do some examples. Let's use the intermediate value theorem. Example 5, which is blue for some reason. Prove that f of x equals x minus cosine of x has at least one 0. So to prove this, we have to use the intermediate value theorem. So we have to go in order. What do we need in order to use the intermediate value theorem? We need f to be continuous on some interval. Is f continuous? I don't know. Yeah, I do know. I do know. X is a polynomial. That's continuous everywhere. Cosine of x is a trig function. We proved that that's continuous everywhere too. So if we subtract two continuous functions, it's going to be continuous everywhere. All right. So that's the first thing that we have to check, right? F is continuous everywhere because x is polynomial, is continuous everywhere. Cosine of x is trig. We showed that it's continuous everywhere. And we can use limit laws. The limit of the difference is the difference of the limits to show f is continuous. So if f is continuous. If f is continuous everywhere, then it's going to be continuous on any closed interval. So that's good. F is continuous on any closed interval. It's continuous everywhere. So any closed interval we think of is a subset of everything. It's continuous on the whole number line. So think of any closed interval. Well, it's going to be, that's part of the number line. All right. One way that you might see this written in further classes is you might say that it is a subset of the real numbers. This means subset, which means it's contained in the set of all real numbers. It's a smaller set that is inside of that bigger set. But you don't need this red thing right now. All right, so f is continuous on that closed interval. That's what we needed for the first thing. Second thing, z is between the function values f of a and f of b. That's a little less clear what we want. What is z? Z is the y value that we're trying to show gets attained. Z is the y value that we want to prove will get hit. So what's our z here? Our z is 0. We want to show that there's a 0. We want to show that we hit a y value of 0. So z, 0, is between f of a and f of b. We don't even have an a and a b yet. We need an a and a b. Z equals 0. It's between f of a and f of b if we need to find f, a and b. And we want that 0 to be between a and b, so we need one to be positive and one to be negative. We need the function value for one of them to be positive and the function value for the other one to be negative, so that 0 is between these function values. So we just kind of have to choose try to figure out what a value and what b value give us positive and negative function values. So let's just start off with 0, because they have to be opposite function values. So for the first point, it literally doesn't matter. The second point just needs to be opposite of the first for that y value. So if a is equal to 0, f of a is 0 minus the cosine of 0, -1. Now is the harder part. It's the harder part now because we have to choose a b that has a positive function value. We need a 0 to lie between the function values. So one of the function values has to be negative and one has to be positive. So how do we choose something that is going to give us a positive function value. And there's a way to cheat. Not actually cheat. Well, there are ways to actually cheat too. I want this to be positive. Well, cosine is always between -1 and 1. Sine and cosine are sandwiched between -1 and 1. We use that a lot with the squeeze theorem. So if I want a positive number, I can just choose a really big X. If I choose like 10, right, I know this will be 10, and we're never going to subtract more than 10 because cosine's never that big. Or we could use like something like 2 pi. 2 pi would actually be maybe a little bit better. However you want to do it. 2 pi we could evaluate exactly. 2 pi is like 6. That's still pretty big. F of b is going to be 2 pi minus the cosine of 2 pi. Cosine of 2 pi is 1. So 2 pi minus 1. That's positive. It's about 6.28 minus 1, about 5.28. But either way, this is negative. This is positive. So 0 is between f of a and f of b. So check, check, check. We have done this part. Oh, we're done. Right? We showed that f is continuous on the closed interval. We showed that 0 is between f of a and f of b. So boom, IVT immediately gets us the rest. All right, so that's how we end. So IVT guarantees at least one C value in the interval from 0 to 2 pi with f of c equaling 0. Again, another way of looking at this, we are done with the problem. Another way of looking at this is saying, I don't necessarily know what this function looks like, but I said this function's negative down here at 0 and positive up here at 2 pi. Since this function's continuous, it's got to cross the x-axis somewhere. I don't know what this function looks like, and it might cross multiple times. But because it's continuous, there's no way to get from point A to point B without crossing and giving us a 0. If you're curious what it looks like, x minus cosine. That's what it looks like. In fact, it basically looks like a line with waves. If you zoom out, like there's an x component, right? And then we're adding a little wave to it because cosine's like a wave. It's basically this line, and then the cosine kind of going through the line. Yes, it turns out there is indeed a 0 in this interval. I've lost. I've gone way past the origin. Turns out there is one right there. And we've proved it. That's how we can prove things with the IVT. So a little bit more complicated than what you may have seen in a pre-calculus class. Do 2 more examples. Let f be continuous on the interval from 0 to 2, with f of 0 being positive and f of 2 being positive. Can we use the IVT here? Can we use the IVT to prove that f has no zeros in this interval? So here, again, to prove that there's a 0, it has to be continuous, and we have to have opposite signs in the function values. We don't have that. But be very careful, because this is not an if and only if. This is not a two-directional thing. This intermediate value theorem gives us conditions to guarantee a 0, but it does not give us conditions to guarantee the absence of a 0. So this can prove something exists, but this cannot prove that something doesn't exist. Okay? So maybe make a note to yourself, right? This can't be used to prove There is not a C. So it can't be used to go the other direction. Our answer is just no. It's just no. Intermediate value theorem can prove a zero under the right conditions, but it cannot prove the absence of a zero. Example 7. If f of x is the reciprocal function, and you can calculate that f of -1 is -1, you can also calculate that f of +1 is equal to +1. Can we use IVT, intermediate value theorem, to prove there is a zero in this closed interval? Well, the IVT does give proof of zeros. Let's walk through the steps and make sure we have them all. Let f be continuous on the closed interval a to b. Do we have that? It's a rational function. Rational functions are continuous everywhere on their domain. Oh, great. So f is rational, rat. So it's continuous on its whole domain. And again, its whole domain is -infinity to 0, union 0 to infinity. Oh. It's not continuous at 0. So it's not continuous on this interval. IVT doesn't apply. We don't have continuity. We almost have continuity everywhere, but not quite. Right? F is not continuous at 0. It's not even defined at 0. And for something to be continuous at a point, the limit has to exist and equal the function value. But the limit's infinity, so we have an infinite discontinuity, and the function value doesn't even exist. So that means it's not continuous on the closed interval. We don't have what we need to use the intermediate value theorem. Because continuous on a closed interval means continuous on the open interval from -1 to 1, and then also one-sided continuity at the endpoints. But we don't have continuity everywhere between -1 and 1 because we're missing it at 0. And in fact, we know that this function looks like this. This reciprocal function looks like this. There is no 0. All right, so even though we're negative over here and positive over here, it's not continuous, so we're not guaranteed that it crosses somewhere. It's not continuous. It goes from way up here all the way down to here. It jumps. It's an infinite discontinuity. That's how we can kind of tie some of these topics together. And that's the intermediate value theorem. More theoretical than a lot of stuff that we've done, but this class is a little bit more theoretical than a lot of the stuff that we've done. Okay, so I realize that things are getting a lot more conceptual. The homework problems for this section are a lot more conceptual. They're going to look a little different than these videos. The concepts are what's important, so you can apply the concepts to new problems. This is a great thing to ask about during student hours, via email, on Canvas, etc. Okay, so don't feel like you have to figure everything out on your own. Send me some questions, and good luck.